Hello, now we will talk about the compressibility factor Z and the deviation from ideal gas behavior. As we said before, that the ideal gas behavior is good if the gas has low density, but mainly we will have large errors as the density of the gas increases. So since water vapor is dense, so we said it is not advisable to assume ideal gas behavior for water vapor. To show you exactly what I mean, this is the TV diagram. So this is a TV diagram for water, and at different values of pressure and different values of temperature. So the numbers seen here at different points are the error. So the numbers seen at different points are the error, and the error is calculated as follows. So the specific volume of the water vapor extracted from the data from the table minus the specific volume calculated using the ideal gas model or the ideal gas law over the specific volume of the table times 100. So this is the percentage of error between calculated data of the specific volume using the ideal gas law equation. So as we said, that P into specific volume equal RT, so the specific volume is easily calculated at RT over P. So for different values of temperature and different values of pressure, we can calculate the specific volume using the ideal gas law and compare it with the specific volume from the mainly the superheated vapor table. So we can notice, for example, at very low pressure, exactly at a pressure less than 10 kilopascal, we have good accuracy, approximately less than 0.1%, and regardless of the temperature. So regardless of the temperature, we have good accuracy. So at a pressure less than or equal to 10 kilopascal, we have an error that is less or equal than 0.1%. So in this region, we can say that the water vapor can be treated as an ideal gas. So also we said that for high temperature and low pressure, means low density, we can still apply the ideal gas law. So as you can see, as the temperature increase, the error will decrease. So the error will decrease. And also, as the pressure decrease, let's say from 5 mega to 1 mega to 100 kilopascal, we have a decrease in the error. So as temperature increases and pressure decreases, the error will decrease. So this complies with what we have said before. Higher temperature, low pressure means low density. So gases with low density can be treated as an ideal gas. However, this error, let's see where the error is large. The error is large mainly near to the saturated vapor line. So as you can see here, the error 152.7%, 49.5, 16. So it is large near the saturated region, and also is high near the critical point. So we need to be well above the critical point in order for the error to decrease to 10. As you see that the critical temperature for water is approximately 374 degrees Celsius. So at like 600 and at a pressure of 5 megapascal, this error is 2.4%. So it is high near the saturated region and near the critical point. So mainly in air conditioning application, the water vapor is treated as an ideal gas. The water vapor is treated as an ideal gas. Since the water vapor present in the air, so this is defined usually by the relative humidity in air conditioning. So the water vapor present in air has very low pressure, so less than 10 kilopascal, so it can be treated as an ideal gas. However, in power plant application where the steam is at high pressure and high temperature, so in this region near the critical point, so we should rely, so in power plant applications we should rely on tables, not using the ideal gas law. Should rely on tables or available data. So this mainly, we said the ideal gas is applicable with high temperature and low pressure. So ideal gas model is valid for high T and low P. But one can ask a question, what is considered as high and what is considered as low? So this is relative for different substances. So this is relative for different substances. So in order to solve this issue, we now define the compressibility factor Z. So we will define the compressibility factor Z. So the compressibility factor Z account for the deviation from the ideal gas behavior at a given temperature and pressure. So this Z is defined as PV over RT. So we can say that PV is equal to Z RT. So this is the actual specific volume for a real gas, not an ideal gas. However, we can always say that PV for an ideal gas is equal to RT. So Z can be written as, here the ideal specific volume is RT over P, and we can always like say that Z is equal to P over RT into the actual specific volume. So it will be eventually the actual specific volume over the ideal specific volume. So whenever Z is different than 1 or deviate from value of 1, we have deviation from ideal gas behavior. And Z mainly is found experimentally. So what we do is we measure the actual specific volume and we divide it by the specific volume calculated using the ideal gas law RT over P for a given temperature and pressure. So since the condition for high temperature, low pressure, and high and low are relative for different substances, in order to resolve this issue, we do normalization of pressure and temperature. So the normalization is done for pressure and temperature, and we define two parameters: the reduced pressure, which is the ratio of the pressure over the critical pressure, and the reduced temperature, which is the ratio of the temperature over the critical temperature for a given substance. So PR is called the reduced pressure, and TR is called the reduced temperature. So it was found that for a given reduced pressure and reduced temperature, for a given reduced pressure and reduced temperature, substances have the same value of R, the same value of Z, So this principle is called the corresponding or the principle of corresponding states. Principle. So it means that the data for the substances, for different substances, collapse into the same graph, and this graph is called the general compressibility chart. So as we go to this graph, this is the general compressibility chart. In the y-axis we have the parameter Z, which is found experimentally, and by measuring the actual specific volume and divided by the ideal specific volume, which is RT over P. And in the x-axis we have the reduced pressure, and the Z is drawn for different values of reduced temperature. So let's try to analyze this graph as you can see that as Z tends to 1, we have less deviation from the ideal gas behavior. So as Z tends to 1, we approach ideal gas behavior. So in this region, whatever the value of the reduced temperature, so for different values of reduced temperature in this region, we can assume ideal gas behavior. So this region is characterized by very low values of reduced pressure. So we can say at very low reduced pressure and regardless of the temperature, we can assume ideal gas behavior. And also we can say at very high reduced temperature, more than 2, this curve approaches unity also. So at very high reduced, so at very high or very high temperatures, mainly at reduced temperature greater than 2, also ideal gas behavior is valid. So let's see where we have a great deviation from the ideal gas behavior. We have a great deviation from the ideal gas behavior as this curve approaches this point. So this point here, where the reduced pressure is equal to 1 and the reduced temperature is also equal to 1, this is the critical point. So near the critical point, we have the greatest deviation from ideal gas behavior. So in the next video we will solve an example using the generalized compressibility chart.